Present. Present. Okay, so this is a presentation about Zcash. So I'm going to start with an overview of the system. Then I'm going to talk about addresses and keys. And then I'm going to explain what nodes are, what they represent, and finally how we do transactions, how we form transactions. So let's get with the overview. Zcash is very similar to Bitcoin in the sense that what it cares about is to capture the account values, account balances. It's not like Ethereum, where Ethereum wants to be presenting a universal computer. In Zcash, the only model that we want to keep, only information that we want to keep, is accounts and account balances. What is interesting though with Zcash is that there are two. Essentially, it's as if you have two coins that are merged into one. The first coin is basically Bitcoin, in the sense that it works exactly the same way. Actually, it is based on the fork of Bitcoin Core, so that part of the system is inherited from Bitcoin. And in that part, you have addresses that are called transparent addresses. And when you make a transaction between addresses from that pool, these transparent addresses, everything will be visible in the blockchain. There is no encryption or hiding of information. So you'll be able to use with the blockchain explorer, you'll be able to see the transaction inputs and outputs and track where the money comes from and where it goes to. In opposition to that, you have a shielded pool where addresses will be hidden. So when you make the transaction, you obviously know who you are paying, but a person who does not a party of this transaction will not be able to see neither the value nor the addresses involved. The very good, interesting point about having these two pools merged into the same system is that you can make transactions that involve transparent inputs and outputs, as well as shielded inputs and outputs in the same transaction. So you can have several inputs that are transparent and shielded, and several outputs that are transparent and shielded. So you can mix and match basically in the same transaction. In the shielded value pool, currently we have two sets of addresses, and these represent the evolution of the protocol. When Zcash was released, their encryption system was called Sprout. So both of them are based on ZK-SNARK, but the first iteration of ZK-SNARK were less advanced, let's put it this way, and the transactions were pretty large. The ZK-SNARK were pretty large. Right now we are at sapling, which is the second iteration of the protocol, and the ZK-SNARK are much smaller and faster to compute. Later on, there will be further improvements to the protocol. The next one is called Orchid. As always, you are able to transfer between different pools. They're called pools because basically, when you make a transaction, you add value to a certain set of addresses that have value in their system. So, for example, Bitcoin has only one pool. So all the 21 million Bitcoin are in this Bitcoin pool. But with Zcash, since you have transparent addresses, Sprout addresses, and sapling addresses, you can take money from one pool and then transfer it to another pool. There's some deprecation going on with these pools because Obviously, the maintainers of the protocol do not want to have to keep so many different protocols in place. So eventually, Sprout will be deprecated. So let's talk about addresses and keys. In Bitcoin, you only have you have addresses that are backing a particular script. So it's very pretty simple model. Most of the addresses that you're gonna see out there are simple pay to hash, public key hash, and these are all the addresses that we start with 1. These addresses are obviously public, since everything is public in Bitcoin. But in Zcash, you will have also shielded addresses. So now I'm just going to talk about the sapling addresses, not the Sprout or the transparent addresses, knowing that transparent addresses work the same way as Bitcoin, except that the encoding is different. So they start with a T instead of starting with a 1. Sprout addresses are not so meaningful anymore, since the Zcash team wants to move away from them. So it's not possible right now to create new Sprout addresses. For backward compatibility, you still can have spending. You can still spend obviously from Sprout addresses, but you can no longer transfer to Sprout addresses. So we have now sapling addresses, and they all when you have an address, it's you have generated it from 1 key, which is a spending key. Then working backwards, what you're gonna give to the people who want to receive money from is your payment address. And the interesting thing here is that there's a diversifier included in this payment address, which means that you can have several different addresses that are actually derived from the same spending key. Actually, it's from the same incoming viewing key. So you don't have to keep track of different accounts just because you want to have different addresses. The people who are going to pay you, even though they will have different addresses, do not have it's going to be the same account behind, essentially, but they will not have the way to know that this is the same person behind all these addresses. You, on your side, you have this incoming viewing key, which allows you to decrypt these incoming transactions. So when you receive money, since the transactions are encrypted, you need that viewing key in order to decrypt them. Otherwise, they will be shielded. There's also the notion of an outgoing viewing key, and that's the kind of the opposite of incoming viewing key, in the sense that it allows you to decrypt transactions that you make on the way out. So if you pay somebody and you forget to keep a record of that transaction, without the outgoing viewing key, you will no longer be able to decrypt the transaction that you made yourself, because the encryption is similar to when we do a public key and secret key encryption. If you encrypt something with a public key and you destroy the original document, you don't have the ability to decrypt a message that you have made yourself, because you wouldn't have the secret key matching that public key. So in order to provide a mechanism that is similar, there is this outgoing viewing key. Again, that allows you to decrypt the notes that you have made yourself to other parties, whereas the incoming viewing key allows you to decrypt the transactions that are coming into your account. Finally, there's the spending key, which obviously is needed when you need to spend from a note that you have, some money that you have received. So all these keys are actually derived automatically from a central seed through a mechanism very similar to BIP32, was standardized by a document called ZIP32. So you don't have to remember all of that stuff. Obviously, knowing that is better in case there's anything that doesn't behave as expected, because at the end, the one and only thing that you need to keep track of is the seed, which is 12 words. Behind the cover, you have actually two additional keys that are called the authentication key, used to sign the message in order to spend, and the nullifier key, which allows the system to create nullifiers. We're going to talk about nullifiers and a bit later in this presentation. Again, the main keys here are the ones that are important, and they all derive from a single seed. You should still remember though that since everything is since transactions to saplings are encrypted, Blockchain Explorer would not be able to show you any information about a transaction that has shielded inputs and outputs. You will see the number of shielded inputs and the number of shielded outputs, but you will not be able to see the amount, either incoming or outgoing, as well as the destination or the provenance. So let's talk about nodes now. So when you're talking about Bitcoin, you have this notion of UTXO, which is the output of a transaction. So when you have a transaction that pays a person, it would take inputs from previous transactions. So the transaction forms a graph, which connects inputs to outputs. Imagine basically that you have a series of wallets or series of stacks of coins, and the transaction is taking several inputs or several of these stacks of coins that you own, put them all together, and we distribute them into outputs. The output could be a stack that you still own, but typically if you want to pay some money, you would obviously create a stack that you do not have access to. So in Zcash, the equivalent of transaction output, or more importantly, is called a node. In the transaction will be then the goal of the transaction. It will be to create new nodes, so and to spend existing nodes. Similar to Bitcoin, a node is not breakable. If you have a output node, that's for example for 100 ZEC, and you need to pay somebody for 50 ZEC, you will have to spend the entire 100 ZEC, but create two outputs. One that is directed to the person that you're paying for 50 ZEC, and another 50 ZEC minus the mining fee, directed back towards you. So you're basically paying yourself for 50 ZEC for the change. When you create a node, the node captures this information, has this property. So obviously you have the payment address. So payment address is a combination of a diversifier and the key, and the public key. That's a value. So the value is the amount that is at the node. And the additional thing that Bitcoin doesn't have is this random commitment. So the random commitment, for like any commitment, this is a value that makes sure that each node is different. Otherwise, you could be having nodes that are identical because you are paying the same person with the same amount. Each node has to be unique in the system. So the system doesn't store all the nodes. The information we saw before, the node plus the memo, because when you create a transaction, you can also associate arbitrary text to your transaction, to your node. That part is something that is personal, or is something that the receiver and the sender can see, but other people cannot see. What they need to keep track though is the node commitments. because without keeping track of the order of anything related to node, there would not be a way to figure out if the node has been, which node has been created and which node has been spent. So the node commitment, so any commitment has these two properties. It allows you to hide the actual node. So when you receive a node commitment, it is linked to a node, but receiving the node commitment doesn't give you any information about the node itself. And the second property is that it's binding to a node. So if at a later point a person reveals the node, you can see that that node is the node that matches the node commitment by calculating some association, some value. So for example, if the commitment is a hash, that will work, because if you hash the text, it gives you no information about the text. But if you afterwards reveal the text, the person can calculate the hash and compare the values, the hash values, and see that actually they are the same. When you have these node commitments, the validator of the protocol has to keep track of all these node commitments, and it has to be stored into a tree. So this Merkle tree, it's a way to store all this information in a way that only one single value allows you to verify that the entire tree has not been tampered with. So let's go now to how to do a transaction. So let's actually work backwards in outputs. We know that the goal of output is to create to create nodes. These nodes will be encrypted, but decryptable by the person that has the proper keys. So either the incoming viewing key or the outgoing viewing key. But not by anybody else. The other thing that the output creates is these node commitments. So the inputs will be the cancellation or the structure, the tombstone for a given node, in order to prevent the linking of transactions to their nodes in a way that you don't want a guy that observes the transaction to be able to figure out which output was spent in that particular input. But you do want to avoid having a node that is spent twice, and you also don't want to have a node that did not exist and that being spent. So in order to solve this problem, they use nullifiers. So when you have the proper keys, so you need this nullifier key, and then you need this authentication key, you'll be able to create a nullifier that is uniquely associated to a given previous spending node. Or more precisely, it would be associated to a node commitment. So that way, if you spend twice, you'll be forced to create the same nullifier, and you'll be forced to publish the same nullifier. By keeping track of all the nullifiers in existence that have been published, the system can avoid having the possibility of double spend. So here you have it. Now we can go into more details. This is basically the overview of the system. You can go into more details about how these components work, but that's a bit more technical. Okay, so let's go back to the first section where we're talking about addresses and keys. We said that you get a spending key, and then from that spending key, which is the something that you can derive by zip32 from the seed, you actually derive a bunch of separate keys. First one is the ACE key, authentication secret key, and the AS key is associated with the A key. So when it's AS key and then A key, it means that this is a pair of secret and public keys. A key is basically ASK multiplied by generated point on a particular elliptic curve. And the same thing is true for this NSK and NK. N stands for nullifier. And finally, you have the OVK, which is the outgoing viewing key. So that these three things, and basically these 5 things, derived directly from the spending key. Then you combine the AK and NK. So now we're talking about public points to form the incoming viewing key, and we will see that IVK and OVK will be used in the process of encryption whenever we create outputs. So the entire full viewing key, the entire viewing key is the combination of the incoming viewing key and an outgoing viewing key. So now for the address. We talked about this diversifier, which is again just a random value d, and by taking d and then projecting it into a curve, we can pick one point on the curve as the generator. So this generator is a point that is derived from d, and then you multiply that point by IVK, you get this PKD, and d and PKD together form the address. So obviously you don't need to remember all of that, but that's the way it works. Now for note, right? So we go back to the presentation. The note was so we talked about this. This is exactly all these elements here. Now we talk about notes. And the node has a payment address. So in that case, it would be D and PKD. D and PKD, the value, and the random commitment. So random commitment, you choose when you create that node, you create a random value and then you hash it to get this random commitment. At one point, you would have to reveal the random value that you have chosen to make sure that it matches the commitment. Then when you want to create a nullifier, so this is a process that you will go through for the nullifier. The nullifier, let's go back up here, is basically what you want to produce in order to show that you have that you're talking about a node that already exists. So every node commitment that you have created, or that is created in general by in the system, will end up in a particular place in this Merkle tree. The Merkle tree has a structure of a binary tree, and it's incremental because you always append. All the nodes will be added one after the other, and this Merkle tree is pretty deep. I think it has 64 levels, so it has enough storage for 2 power 64 nodes, which is more than needed right now. So that node, if you know, because you're spending an existing node, so you know which node you're talking about. For all the other people, they have all these node commitments, but for 99.9% of these node commitments, they do not have the matching node. You want to spend a given node, so you know which node you are talking about, and you know which node commitment it is. So therefore, you would know where that node commitment is in the tree. And everybody agrees on the order of insertion of these nodes. So everybody has the same Merkle tree. Everybody has the same for the same placement of these node commitments. So you are going to designate your node by pointing to a given node by its position. That's P or rho, and then with that P plus the nullifier deriving key, you can form the nullifier. So that shows that you know where the node is, and that you have that special key, this NSK. So you know where the node is, plus you have the authority to create a nullifier. And the second thing that you have to provide is a signature to also show that you have the authority to sign, to spend. All right, so that's about how you create the spending part. How you create this new node, and now we're going to talk about the encryption base for the encryption for the spending node. It's again it's pretty similar. You have the node plaintext, right? So the node we know that it's the it's this thing. Why is it? Oh, this is pretty lame actually. Okay, so the node is the address, right? So with D and PKD, it's the value, and it's the node commitment RCM, and there's a memo. Okay, so this is all the stuff here actually, right? So you will provide. Okay, so these are the node commitment is going to be plain text as and clear as we said before. CV we didn't talk about, but let's talk about this just afterwards. And then you have the node plaintext, which is what's the thing that you're going to encrypt. So the interesting thing here is that you want to encrypt in a way that the guy who has IVK can decrypt, and the guy who has OVK can decrypt. So what you do here is you create a temporary, so it's called an ephemeral encryption key. So you choose a value randomly that will be only used for this particular output. Then you form the matching public key, multiplying by GD, and we remember that we also have this relationship with IBK. So EPK is ESK times GD, but PKD is also IBK times GD. So by the fact that you have this relation, you can derive a share secret, which is the basically the multiplication of the public point with the opposite secret key. So either you do EPK times IBK, or you do ESK times PKD. In both cases, you will have the same result, which is this value. This is going to be your agreed secret that you can use to encrypt. So what about the OVK? OVK would be also used to derive a second encryption, which is going to be cout. So the first one iscenc, the other one is cout. And with cout, what we do is we encrypt PKD and ESK, because if you know PKD and ESK, right, then you do not need to have IVK to decrypt. You can also do this PKD times ESK times GD, right, and then you will have the same secret here. So in the person who receives the node uses the relationship EPK times IBK, but the sender will use the relationship ESK times PKD, which leads to the same value. So if you have a way to get this guy, then you can decrypt, and you can get this guy because it is encrypted with the OCK, which is calculated from the OVK. So at the end, the output will be a combination of CV, CM. So these are the parts are in clear, as well as the ephemeral encryption key, and then the two encrypted parts. CENC will be for the receiver, and cout will be for the emitter, in order to retrieve the shared key. So the last point we talked about is CV. Actually, CV is used in both sides. It's used in the spending side, so inputs, and then also as the outputs. So inputs will have CV, nullifier, and the anchor, and the signature. So that's a bunch of things. But CV, what is CV? CV is a commitment on the value. The interesting part with the particular commitment that they have chosen is that it's stable. in respect to addition. In a way that you can check that inputs and outputs values balances. So inputs and outputs balance. So if, for example, you spend 5 SEK in input, you have 5 SEK in output, but without disclosing the value. So if you say you take 5, let's say you have 1 plus 2, and then okay, let's say you have 1 plus 3 and 2 plus 2. If you transfer that to their commitment, to their value commitment, so 1 can become 1 million, and 2 becomes something else, and 3 becomes something else, and so on and so forth. The relationship between the commitments remains the same. So even though you can do the summation on the commitments instead of on the original value, the equality remains. And finally, that allows you to check that the transaction does not create or destroys value without having knowledge of the actual values. There's one more thing here that is missing, is the binding signature, and it has to do with the fact that it's not as simple as that, because you also can transfer from other pools. So it doesn't exactly balance between in the sapling pool and the shroud pool, because the equality is not like you have exactly the same amount in inputs and outputs from a given pool, but there's another element, the binding signature, that allows you to account for that discrepancy. So here you have it. I think this is pretty much it. That's pretty complicated, as you can see, but from a really high level, the key takeaways is that it's a system that is very, very similar to Bitcoin. It tracks nodes and node values. The things that they have brought is the ability to encrypt the nodes. So contrary to other systems like Monero or Dash, the outputs are entirely encrypted. So there is no obfuscation involved. The data is really not available unless you have the proper decryption keys. Though the way for them to make sure that even though it's encrypted, the relationship for a valid, correct transaction stand, like equality of the values, the fact that you're not double spending, the fact that you are spending from an address that you own, which is the basic properties of a transaction. All these things are verified through Zcash Dark. So we haven't talked about Zcash Dark at all, and it's a topic that is very complicated. So I don't think it brings too much here. But the idea is that you can, if you have statements that can be expressed as a series of equations, like in that case, it will be that, for example, the ACE key, the authentication key that matches the A key that is involved in something, right? So you can express that as a function, and that function to hold true. Then you can provide a proof that statement is true, giving the proper secret inputs. So the values that you hold, the secrets that you hold. You can prove that you hold these secrets without actually having to provide them, and without giving any information about what they are. And there's a lot of flexibility in the statements that you can include as a Zcash Dark. The only limitation currently is compute related. Some of these Zcash Dark processes are extremely long and hard to calculate, so it takes a long time for the proof to be generated. And the second thing is they are too large, so it takes too long, and they are too big. So when you provide the proof is very large. And the third thing, and that's the current limitation now, so they came out with a solution for number 1 and number 2. The third one is that there's a lot of pre-calculation involved in forming a zk snark, and currently you have to make the zk snark based on a particular statement. You can't just say that this is a dynamic program, it's a program that changes, like this is a smart contract, and instead of proving that I have executed smart contract properly, I just give you the zk snark. That's currently not possible and with the system that they use in Zcash. The statements that they are providing zk snarks for are the statements that validate the transaction, and they are in a sense fixed statements with inputs that are variables. So obviously the inputs are variable is the value, the keys, the address, and so things like that. But the statement that they want to prove is the same one. And once you have the statement, you can go run it into a zk snark processor, and that gives you a particular algorithm to generate the proofs and to verify the proofs. Also, the last annoyance with this with the current system is that it relies on the existence of a set of parameters that are derived from these particular statements, and these parameters are calculated from a secret, but nobody should have access to that secret anymore. So you have to derive particularly public key, something that behaves like a public key. But you have to make sure that nobody has the matching secret key. If somebody had a secret key, he could create proofs of statements that are wrong. Okay, so that's pretty much it. I think that we have covered most of the things that are relevant for the existing implementation of Zcash. All right, I'm just gonna stop here then.